work, you know, as this every time this counter clicks, it's done a block of work. Okay, block, 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 block. It's still working, but the main thread is handling the UI operations, and the child thread is handling that work. And eventually, the child thread comes back and tells the main thread, "Hey, I'm done." So we'll see how that happens. So this is just a motivation for threading, why we might want to think about threading. So we're going to start out talking about the way Windows works to give ourselves some background for the rest of the conversation. Let me point out, we're not going to get to this, C++ 11 concurrency. These are demo examples. We won't get to them today, I don't think. I didn't earlier on the first class this morning. I'm going to make a contract with you that if you understand what's in this folder, you're ready for the midterm as far as the threading goes. Okay? And you say, oh, good. Well, if you open it up, you'll find there's 13 projects and a solution in there. Okay? But they're all short. You know, so. And we're going to cover the whole thing on Thursday. And we'll talk about it again more if you need to on Friday. Okay? So while there's a lot of material, if you focus on this, you know, that'll take care of the midterm. You know, there's other things. We're going to talk about a blocking queue. There's a thread pool down below. I'm going to talk about those things. They're things that I wrote that are going to be very useful for us. But as far as the midterm goes, this is what counts. I won't ask a question about the blocking queue. I won't ask a question about the thread pool. Okay, so let's look at this process diagram. So this is my mental model for a process. So this outer rectangle represents a process. And in that process is process code. There's a code segment. There's global memory that's shared by threads. There's thread stack. So up till now, we've talked about thread stacks like there was only one in a process. So main function pulls down a stack frame. And if that function calls another function, that pulls down a stack frame, pulls down a stack frame. So we have this stack of frames that the individual functions are. But when we run multiple threads, each thread has its own stack frame. Turns out that's very important. One of the consequences of that is that any local data that's stored in those functions in that stack frame, they're unique. So if I have two threads running through the same code, but their history is a little different, they may have different values for the local variable, and they are absolutely unique. Each thread has their own values to those local variables. There are things it shares, you know, any global data it shares. If it's the threads are running in member functions of a class, they're sharing the member data. Okay, so. So there's process code, global memory, thread stack, and then heap allocations. You know, you can ask the operating system, give me a heap. By default, you know, there's a default process heap, but your code can ask it for another heap if you want to. Typically, we don't do that, but you know, .NET does to create the managed heap, for example. Here's a DLL that this process loads, so it just adds code into this process code. There are windows that this process created. Unlike Linux and Unix, Windows creates, the operating system itself creates Windows. In Linux and Unix, Windows are created by a layer, a drawing layer that used to be based on X Windows, but some of the more recent versions, there's a new window manager. But anyway, they're not part of the core operating system. In Windows, it is part of the core operating system. Maybe that's why they called it Windows. Okay, so And there are threads. So here's the main thread and a worker thread and window and window. And what's happened here is the main thread, so every process starts up with one and only one thread. And typically that thread is the thread that creates windows. But whatever thread that created the windows, that thread will pull messages, respond to messages that are sent to that window. Only that thread that created the window. When a thread creates a window, it gets associated with it a message queue. And it pulls messages out of the queue. A worker thread is not allowed to directly access elements of these windows. And the reason for it is that no locking is done on these windows. If we had locks, that main thread that's supposed to be listening to the user events would block and the screen would freeze. So no GUI, none locks code in the main window, locks window code. WPF doesn't. Windows internal, you know, the Windows window doesn't. Java FX doesn't. You know, Java Swing doesn't. Linux Qt doesn't. You know, none of them do, because they don't want the window to block. So what that means is that worker threads are not allowed to directly access the window. But what they are allowed to do is post messages or send messages to the window. Each window has a message queue. We'll see that in a minute. And so each window has this queue and expects multiple concurrent users to be dropping messages in the queue, but only a single thread is pulling messages out of that queue. So there's never any conflict in here because there's only a single thread that's running the code in that window. Now, you might be looking at this and saying, okay, but what's all this handle stuff? Module handle, heap handle, thread handle, window handle, process handle. What's all this handle stuff? Well, it turns out that each of these are objects in the operating system. A window is, a thread is, a process is. They're all operating system objects, and those move around. And they are accessed through this handle. So, for example, heap, you would tell the operating system, you'd say create heap, and it would return you a handle. And you could call create heap again, get a different handle. Okay, and this is very object-oriented. That part of the API for heaps is like a heap class, and each down in the kernel there's a little bit of memory associated with each of those heaps, and the handle is like the this pointer that points to that specific object's data. So, but Windows moves these things around. So, for example, a thread may move around, a socket may move around, you know, different places in memory. I'll explain why in a couple of minutes. And so, what happens is Windows doesn't want to go and adjust each of those handles when an object moves. That would be very process intensive. So instead, Windows has an address table. All these handles are pointers or references, are indexes or pointers into that address table. And when Windows needs to change an address, when Windows moves some object and needs to change the address of that object, it suspends any threads that are maybe accessing that table, makes the change, then resumes the threads, and so your application has this one invariant handle, but the place where the object resides may be a whole bunch of different places over the course of the running program. We'll see how that works in a couple of minutes. So that's a process. That's a process. Okay, so let's look at memory map files. So Windows, like almost all modern operating system, is a virtual memory system. And so we have physical memory, and then each process has a virtual address space. And this virtual address space appears to this process to be a linear, everything is filled, you know, just from top to bottom, all my stuff is here. But that's a fiction. So here, this, so these are really pages of memory map files. So this page, A refers to a slot in this physical RAM, a page-sized slot in this physical RAM, but B is paged out to a page file. Doesn't appear, isn't in physical RAM. But should my code in A make a call into the code in B, that's a page fault, and what happens is the operating system will suspend your process, will map B into the first available slot, maybe right there, okay, in the first available slot, and then turn you back on. And what happens is the operating system code and a little bit of hardware collaborate to create this fiction of this virtual address space. So as far as your program, so, you know, it's always available, always linear, always has stuff in it, and nothing could be further from the truth. But your program doesn't know. Doesn't matter. So, so these, you know, these pages are coming and going out. So when Windows starts up another program, it may look at its available RAM and say, "Oh, we're running a little low, so I'm going to page the least recently used page out of your current running program into the page file, and I'm going to use that slot to put my first page of this program I'm trying to start up." So the other interesting thing is that a process can ask for a page, there's a part of the API that creates a page, and so a process can say, you know, create me this page and give it a name. And if this process says create a page and uses the same name, instead of, so let's say this process did it first, then this gets mapped somewhere in the physical RAM. And now this guy says, create me a page with the same name. It doesn't create a new page, it gives them a reference to that same one. So now they can share that memory. These two processes can share this page in physical RAM. And pipes work that way. Pipes use shared memory, and, you know, name pipes and other things, you know. So really fast, kind of messy. You got to be careful, you know, communicating for reasons we'll talk about today. But. So that's memory. And then the last part of that recipe is Windows message processing. So here is a particular window that our process created. And the thread that created it has this message loop, and this is the thread that created this window. Whatever thread creates this window, he gets this message loop and he starts pulling messages out of that message loop. The message loop starts up and he starts pulling messages out of the message loop. And at first, he'll just block, nothing there. And over here is a bunch of physical devices hung on a machine, and each associated with each device is a interrupt service routine or device driver whose job is, very quickly, if there's a change in status on the keyboard or on the mouse, create a little message and drop it in this raw input queue. Got to be quick because he's got to suspend interrupts for that device, you know, and quickly create that message, drop it in the queue, and turn the device back on. And so I can sit there banging on the keyboard, waving my mouse around, clicking the buttons, and it looks like it's all happening concurrently. In fact, they're just little messages that keep blip, 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 blip into that raw input queue. The Windows Manager pulls, you know, messages out of the queue, and it's got a stack of windows. On the top of the stack is a window in focus, whichever is, you know, not obscured by anything, is currently, you know, got the mouse pointer. And there's other windows behind it that may be partially obscured or totally obscured. They're lower in the stack. And what happens is in comes a mouse message. And the window manager drops it down through its stack of windows, and the first window says, I can't handle that message. The mouse coordinates are not inside my client area, can't handle it. Goes down to the next window. That next window says, yep, I can handle it. That mouse is inside my coordinates. And so for that second window, in comes the message into his queue, and this guy now becomes on the top of the stack, okay, and he's in focus. Whatever window is in focus, by default, gets all of the keyboard events. Every key that's click, 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 they all go into the window in focus. So this is the way it works. You know, there's a whole bunch of windows here. And if no window can handle the event, that goes to the screen, and the screen does whatever it does with unhandled messages, probably dropping them on the floor or whatever. You know, there's a default processing for messages. Depends on the message type. That's how Windows works. You got a really good model now of how Windows works. So, so now with that background, let's talk about threads. Let me pull up a, yeah.
Is the Windows Manager interface which will forward requests to appropriate interrupt service routines?
Beg your pardon?
Is the Windows Manager the interface which forwards the request to the appropriate interrupt service routine?
No, the interrupt service routines are all triggered by the device. The device, when something happens, that device has an interrupt associated with it, and that triggers the device driver to create a message and drop it in the raw input queue.
But there's a common buffer for all these devices.
There's a raw input queue, and that Windows Manager is pulling messages out of the raw input queue. It doesn't know anything about those devices, it's just pulling messages out of the input queue. Single responsibility principle. Okay. So threads and locks. So the Windows API, is used to create, style, and manage windows, manage files and directories, create and manage processes, threads, and synchronizers, load and unload dynamic link libraries, create, manage timers, read and write to the registry. These are main things. There are three principal libraries: Kernel 32 DLL, User 32 DLL, and GDI 32 DLL. When Windows was a 16-bit operating system, they were all Kernel 16 DLL and User 16 DLL and blah, 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 blah. When they went to a 32-bit operating system, they changed them all to Kernel 32, and that caused so much breakage, they said, never again. And so sure enough, on your 64-bit machine, it's Windows 32 DLL, okay? So, those three main DLLs handle most of the stuff. And there's probably 483 other little DLLs, doing all kinds of things all over the place. But the three main things are Kernel 32, that's managing their kernel operations, User 32, that is managing windows and things, icons and menus and things that people see, and GDI 32. And GDI is a graphics device interface. It's a really nice idea. So if your code is writing to a nice 40-inch display on your desk, and that same code later on today is going to run on a 13-inch screen on your laptop, you really don't want that code to have to say, well, if you are sending to a 40-inch display, do it this way. Well, if you're sending it to a 13-inch display, do it this way. It doesn't want to do that. Code just wants to write. Don't bother with me with the details. OS, you take care of it. And that's what the GDI does. All the programs write to the GDI, and the GDI just uses the device driver. So, out comes somebody with a 78-inch screen that you want to put on your desktop. Okay. We always lust for bigger and bigger and bigger screens. It will provide a device driver, and that plugs into the GDI, and the GDI now knows, because the manufacturer of that 80-inch display took care of it for you. Okay. So, cool. All right, so Windows processes are containers for threads. They are not scheduled. Unlike Linux and Unix, processes are not scheduled. Threads are scheduled. In Linux and Unix, threads really are processes. They are a process that forks in a way to share the parent's memory. Okay. And in the old days, 3 or 4 versions ago, if you created a new thread and you asked the main thread what your process is, and you asked the child thread, same code, what your process is, they'd give you 2 different answers. They really were a different process. Now, they give you the same answer. But it works still the same way. They're just, papering over, they're providing this model of a thread, but it's really a process. But in Windows, threads are genuinely distinct objects. Windows are not scheduled, threads are. Every window starts up with one primary thread. Windows contain file handles, other Windows objects, allocated memory. So for example, you are writing code, you're at work, you're writing code that's going to go in some process, and your colleague sitting in the next cubicle is also writing code to that process. And you are using files, and you create file, bam, 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 create file after file after file, and you don't close any of them. Now your colleague has written code that tests fine, works just great. As soon as he combines it with yours, it doesn't work anymore because you hogged all the handles and you didn't close them. You don't own resources. In your academic programs, you own them. But when you work professionally, you don't own those resources. You're sharing them with everybody else who's writing code for that process. So you need to be a good neighbor. What the model is that you deallocate resources as soon as you're done with them. That's one reason why I like C++ so much. I prefer it over C# and Java, because I can deallocate stuff. I know it's deterministic. I can cause it. Yes, bam, return. With C# and Java, I can write a finalizer. I can write a dispose function that will return when that function is called, but every user of your class has to remember to call dispose, and they won't. I write a lot of C# code. I use a lot of disposable objects. I don't remember to call dispose on most of them. I've looked at a lot of professional code. They don't remember to call dispose on their disposable object. So that means that there's a lot of resources that aren't being immediately returned. Yeah, eventually, when the garbage collector gets around to it, it's returned, but it could be for a minute and a half, that database record is locked, even though you're not using it anymore. So, but anyway. So, Windows objects. Windows supports internal objects and provides an API to access them and manage them through handles. Each of the Windows objects has a create function that returns a handle. And again, think of that create function as a member function of some class that represents that part of the API, and the handle is the this pointer to that internal object. Kernel objects, named, secured, system-wide, things like devices, files, symbolic links, and registry keys. User objects are windows, menus, icons, and hooks, are not system-wide. GDI objects, drawing objects, brush pen, device context. Device context is really the guy that did what I was talking about, given this universal palette, we interact with it in the same way, but the devices respond in different ways. It's through this device context. So, I've said all this, so let's go on to the next slide. So, the Windows API provides functions which create an object that return a handle, get an object handle using some other information, get and set information about an object, again using the handle, close the object handle, possibly destroying the internal object. These handles are reference counted, so if you're the only one that has that reference to that object, then the object will be destroyed when you close it, otherwise it won't. kernel objects have security functions that manage access control lists. And there's one more thing that kernel objects have that's going to be very important for us today. They have a signaled state. So kernel objects are operating system resources like processes, threads, events, mutexes, blah, 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 blah. They have security attributes and a signaled state. And that signaled state, if an object is unsignaled, any thread that waits on its handle will block. And there's a function called wait for single object that waits on a handle and it blocks. When that object becomes unsignaled, when that object becomes signaled, the signal object in the signal state will not block a thread that called wait on its handle. So a thread, we can get a thread handle if we create a thread with a Windows API, and we can call wait for single object, and that will block until the thread becomes signaled. It becomes signaled when the thread exits the function you gave it to run on, and that kills the object and that kills the underlying thread and signals the kernel object, and now you fall through. Okay, now you unblock. Yes?
Is it similar to mutex implementation?
Is it similar to what?
Mutex implementation?
Mutex has used this. We'll get to that. Okay. So thread is a path of execution through a program's code. A thread lives in only one process. A process can have multiple threads, but a thread is associated with one and only one process. Each thread has its own call stack, but shares process code and global data with every other thread. When we start a process, the process creates a primary thread. There's a little example I put in the Project 2 Help Spring 13 to pop up Notepad, and that just uses that process starting mechanism. You're welcome to take a look at it if you want, and you're invited to look at it. We're not going to talk more about that today. I have a bunch of words about scheduling threads, but let's look at the diagram. That really explains it more clearly than the words. Windows has a set of queues with different priorities. Highest, blah, blah. There's actually 7 priorities. Surprisingly, there's a priority higher than highest and a priority lower than lowest. Way to go, Windows. Fantastic. Here's what happened. You know, there were 5 priorities from lowest to highest. Made sense. And then Windows spied this very lucrative government contracting for real-time operating systems. And the Windows guys said, oh, we'll become a real-time operating system. Give me a break. Okay, Windows never, ever could be a real-time operating system. But they created this time-critical and idle priorities. Time-critical higher than highest, idle lower than lowest, and tried to peddle Windows as a real-time operating system. And the contract, said, go away. Give me a break. I'm not even going to read your bid. I know Windows can't be real time. Okay, but anyway, here's the way it works. So we have these queues, and what happens is when Windows, so these queues each hold thread control blocks. This is information about a thread. It's not a thread itself. It's information about a thread. And what's held there are the contents of the registers, stack pointer, instruction pointer, blah, 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 and a quantum, how much time you have remaining to run. And when it's on the queue, it has the default normal quantum. Yes, you have a question?
So it's simply round-robin scheduling then. If it uses a time quantum, then it's simply round-robin scheduling.
This is not round-robin scheduling. This is not round-robin scheduling. What Windows does, and I'm going to get to that, what Windows does is it goes to the highest priority queue. When it wants to start a thread, it goes to the highest priority queue. If there's anything in it, it runs that. It takes that thread control block, and gives it to a thread and runs that thread. If that queue is empty, it goes to the next highest thread queue. If that queue is empty, it goes to the next. A thread in the lowest will never run unless every queue above it is empty. No round robin here at all. Now, Windows does do a little gerrymandering of the priorities to try to prevent a low priority thread from never running, but no guarantees. A low priority thread may, in fact, never run. Windows is not fair. It does not use round robin. Okay, so now when a thread, so the Windows goes and it sees a thread control block on the queue, pops it off the queue, and populates it appropriately. So most of these, if this isn't if this thread has been running, its register contents or whatever was in the register when it was stopped, blah 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 blah, and now it has a new quantum, full quantum, and so it'll run, and it may run until its quantum expires. If that happens, if it runs until its quantum expires, it just goes and gets put back at the beginning of its ready to run queue. Each of these are ready to run queues. Goes back to the beginning of its ready. Doesn't run immediately. It won't run until the operating system is ready to run another, and it's at the end of this queue. It's worked its way from the input side to the output side of the queue. Okay. Now, the thread control block has a reference to a process control block that has information about the address space and has files and heap mappings and allocated handles and all that stuff. So every thread shares those. They all have access to that. Now, there's other reasons why a thread may stop running. If a thread blocks, perhaps by calling wait for single object, or on an I/O operation which does the equivalent thing, okay, if the thread blocks, it goes into this pool of blocked and suspended threads. Should that handle that it's blocked on become signaled, then it doesn't start running again immediately. It goes back to the end of its ready to run queue and waits its turn, has to work its way up through the queue. Also, a thread can be suspended. One thread can suspend another thread, and that puts it into the suspended pool, and it won't run again until it gets unsuspended. Now, there's a suspend count, so if on thread 1, thread 2 calls suspend, and thread 3 calls suspend, its suspend count is 2. Now, if thread 4 comes along and says resume, resume, it starts running, even though thread 2 and 3 think it's suspended. Okay. Okay. The Windows documentation says you really shouldn't suspend threads. Not a good idea. Okay. They don't want you to. They do a lot internally. When they change information in the address table, they're going to suspend threads. But they really don't want you to. That can have undesirable effects. Okay, benefits of using threads. Keeping user interfaces responsive. We already saw that generating a child thread can help a user interface remain responsive. Your program may need to respond to high priority events, so you can assign the event handler to a high priority thread, take advantage of multiple cores available for computation, avoid low CPU activity when a thread is blocked waiting for the response from a slow device or human. You're sitting at the keyboard, very fast typer, I'm the fastest typer in the world, blah, 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 blah. To the computer, there's a eon, a whole glacial period between each keystroke, dinosaurs, and now the beginning of the primates, and, blah, blah, blah. It's an enormous amount of time. While it's sitting there idling, saying, please give me something to do, please, please. Okay, so threads can keep the CPU active, use it productively. We can take advantage of multiple cores. These days, almost all machines have multiple cores. Avoid low CPU activity when a thread is blocked, waiting for response. Okay, I already said that. Support access to server resources by multiple concurrent clients for processing with several interacting objects when the program may be significantly easier to design by assigning one thread to each object. It's the idea of an active object that manages its own activities. Here's a typical application. So in a communication channel, it turns out we need threads really badly because almost all channels have an internal buffer at the receive end, and if the sender fills up that buffer, this thread talking to that channel is going to block. And if the receiver thread, if the sender isn't sending fast enough, the receiver empties out that buffer. If it makes another call to the buffer, it'll block until something appears in the buffer. So we really need threads to manage that. So now the main thread in this process number 1 can be making up messages and keep dropping them into a queue that this guy's going to read, and going off and doing other activities. And the same thing here. Okay, this guy can go off and process a message while it's waiting for other messages to come, or do other activities. Our communication channel we're going to develop for Project 3 and use in Project 4 will work this way. Yes?
Or if you say we're using the process class, are we required to do a mutex on it?
I will talk about all those things, but you got to wait, okay? I will talk about them, I promise, but you got to wait for a few minutes. Potential problems with threads: conflicting access to shared memory. So suppose that I have a thread that's writing a double and another thread that's reading it. C++ statements or C# statements or Java statements are not atomic. Maybe to write that double it takes 24 clock cycles, 24 machine statements. Okay? And so my write process has gone through 13 of those 24, and then the quantum for that thread expires. And the reading thread comes along and reads that data partially written. If we're lucky, it'll sense that it's malformed and will throw an exception. If we're unlucky, it'll take that bad data and just operate on it like it's good data and send it all around your application. You're sitting there, why am I getting these weird results? What happened? Is there a problem with my algorithm? I must have a bug in my algorithm. There's nothing wrong with the algorithm at all. Okay? It's a sharing problem. So that's a real issue, and so the operating system gives us lots of ways to manage that with locks, like mutexes. Okay, there's a bunch of them. We'll look at the family of locks, but essentially, one thread acquires a lock, and then begins writing that. And if its time slice expires while it's writing, even though it goes to sleep, it holds that lock. So another thread blocks when they try to read until the first thread wakes up again, runs to completion. Now it releases the lock, and the reading thread can now read it. Problem solved. Way to go. Race condition. So this is a race condition, but I like to use the term race condition for more global things. Correct operation depends on the order of completion of 2 or more independent activities. So let me take a simple example. Thread 1 is creating an object and initializing it. Thread 2 is going to use it later on. A maintenance programmer comes along and adds absolutely correct code in the path of that creation and slows it down. So now the using thread gets to it before it's properly initialized and with undefined behavior. That's a race condition. They are incredibly difficult to find. I have thrown code away I had worked on for 2 weeks because it had a race condition that I couldn't find. But there's a worse problem. You may not realize you have a race condition because it didn't get triggered while you tested. You shipped it to your customer, and a month later, he's pounding on your door. You idiots, can't you write decent code? Blah, blah, So, because the race condition was triggered, right? a Canadian company, Therac, I think it was, built X-ray machines. And they were using threading to control dosage levels. And they killed 8 people with massive overdoses because of a race condition. You're designing the flight navigation system for the Boeing 797. Race condition. Boom! Boom! 243 people died, and it's your fault. Okay? Your fault. It is. So because that's so serious, the operating system gives us lots of help for that. Wrong. None. Zero. Zip. Nada. Nothing. Why? Because it would be incredibly expensive to do that analysis. That may even be Turing incomplete. I don't know. Okay? Maybe like a halting problem. Who knows? Okay? So, not going to do that. So it's your responsibility. Your responsibility. Are you getting worried? You should be. Starvation. High priority thread dominates CPU resources, preventing lower priority threads from running often enough or at all. Priority inversion, low priority task holds a resource needed by a higher priority task, preventing it from running. Deadlock. Thread holds a resource and wants another. Thread holds a resource and wants this one. Deadly embrace. Okay? They're both blocked, waiting for the other to wake up and release the resource, and it never happens. And it's probably not that simple. It's probably thread A wanting a resource from thread B, wanting a resource from thread C, thread D back to A. Okay, some complicated network, and hard to find. I try never to ask for a resource on a thread that's already holding a resource. It isn't always possible, but I really try hard not to. If I do that, if I'm successful, so if I have a resource, I don't ask for another one, then I can't deadlock. Can't happen. There's also a scheme for doing a hierarchical management of locks to prevent deadlocks. You know, that's beyond the scope of our conversation probably this semester. But so, so now we should be beginning to understand that these aren't so serious. We can normally deal with these without too much trouble, but the race condition is a serious issue. Imagine, you know, here I am at work, and one day my boss comes in, puts his arm around my shoulder and says, "Jim, I got a new project for you to work on." And he trundles me over to this new office. So I sit down, he gives me the docs, I start leafing through the documentation, and I see a complicated threading model. You know what I'm going to do? I'm going to reach into my desk drawer, I'm going to pull out my resume, I'm going to polish it up, I'm going to send it out, because that project's going to fail. That project is going to fail. And I don't want to be associated with a failed project. I'll quit. Yeah, that's not a joke. I would. So what do you do? So the moral of the story is keep your threading model simple, simple, simple. And you say, how do I do that? You do this. Here's a simple threading model. This thread. So I've got a thread-safe blocking queue. He pulls a message out of the queue, sends it into the channel. This guy, all he does is frame a message out of this channel, put it in the queue. That's all he does. He's only interacting with these other threads through this thread-safe blocking queue. That turns out to be a very safe, manageable, understandable, analyzable threading model. And I emphasize that in my classes. We don't use RPCs. We use message passing communication between threads, between processes, between machines. That's what we do. And it's by far the safest, sanest way to implement nicely flexible, high utilization, software that can keep all the cores you give it busy. Okay, nice way to do it. That's going to be a recurring theme in this class: message passing communication. Another issue here is UI workers and UI and worker threads. So user interface threads create windows and process messages sent to those windows. Worker threads receive no direct input from the user. They must not directly access a Windows member functions. Okay, in a lot of frameworks that'll cause exceptions. We're going to use WPF to build our GUIs in this class, and that's exactly what happens in that framework. Worker threads communicate with the program's windows by calling the Win32 API post message and send message. As I showed you in the process diagram, child threads are allowed to post or send messages to another window. That's perfectly manageable and acceptable. The reason they're not allowed to directly access the window is that window isn't locked. Can't be locked because we don't want it to block. And if we directly accessed, guess what? We'd have race conditions, deadly race conditions. So all windows work that way. They have a message queue that can accept multiple concurrent clients dropping messages into the queue, but one thread pulling them out and executing them and managing the window on that thread. It's called a single-threaded apartment model. You'll hear that term if you take distributed objects in a year from now.
Professor?
Yes?
When you say worker threads, you're referring to every child thread other than the main window thread in that context?
Yep. Only the thread that created the window is allowed to process code in that window. Okay. Creating Win32 threads. So the API for all of the kernel objects, the thread is a kernel object, has a create function. There is a create thread function that returns a handle, and you shall not use it. Here's why. That create thread function does not initialize the C or C++ libraries. Does not. And so if you expect to use C++ or C libraries and you call create thread, you'll find that a whole bunch of those library functions don't work. Some of them appear to work but work incorrectly. Some of them don't work at all. Some of them work correctly. Who knows? Nobody has the complete list, okay? So you say, so what the heck is, what's the purpose of that? Well, Microsoft developers who work on the Windows team don't use, for performance reasons, don't use those libraries. They use the Windows API, and the Windows API is complete enough for them to do everything they need to do to manage Windows development. Everything they need to do. This string management, all the kinds of things that are in the library APIs. Guess what? The library APIs are based on the platform APIs, and anybody that calls create thread has to use the platform APIs because those libraries aren't. So it makes sense for Windows developers, but the rest of us, we don't want that pain. There's a lot of pain there. If you're doing it every day, there are, last time I counted, about 12,000 functions in the Windows API. More by now, I'm sure. Do you want that pain of understanding which of those 12,000 functions you want to use and how to use it? I don't want that pain. Now, I occasionally write code to the Windows API, but I vastly prefer to use the libraries. The only time I do is when I'm trying to do something. I create libraries. You're going to use my file system library. I wrote file system for Windows and I wrote file system for Linux. So I could write common code that used file system, exactly the same interface, whether I was running on Windows or Linux. So I would write to the platform APIs in that case, but I'm not going to, absolutely prefer to use the C++ libraries. So the Visual Studio team wrote these functions, begin thread. There's another one, begin thread EX. And the way they work is it does return a handle, but these initialize the library. I'm certain underneath they call create thread, but only before initializing the library. Only after initializing the library. So, and you pass it a thread function that has this particular signature. Notice it takes a void star. You say, what's going on here? Why do that? That's not type safe. What's going on? And here, we pass it a thread info, same thing, okay? So this is the address of thread info is this pointer. So now, what's going on here is the creator of this thread library, begin thread function, they don't know what function you're going to pass it and what arguments it needs. How would they know? So their model is that we let you use a void star pointer that is going to point to some structure that you're going to pack with the arguments you need for your function. Now, you wrote this thread function, okay, and you wrote this struct. The application wrote this function, and the application developed that struct. So when you're inside this function, you know how to unpack it. It's coming at you as a void star, and you cast it to your structure type, and you pull out the parts. And it works just fine, thank you. Okay. That's the way this works. And this only works, the Windows API only works if you pass it a unbound function, a global function, or a static member function of a class. It doesn't work with non-static member functions because non-static member functions pack the this pointer at the beginning of the argument sequence. You don't see it. It isn't in the calling argument you wrote, but the compiler puts it there in that sequence of arguments, and now the code that in the operating system uses it, it doesn't know anything about this pointers. It's a C API, and so it gets totally confused. It has this argument, it's totally confused about. It tries to use the this pointer as the first argument for your function, and that sort of stuff. So anyway, it provides those functions, and you will use them if you write to the Windows API. So we create, there's a function begin thread EX. It adds a little bit. It adds security attributes, and it adds this nice init flag that lets me start the thread running or start it suspended, however I want to do. I tend to like to start thread suspended so that I can twiddle with the priorities and set properties and stuff like that before I use it. It turns out that this, you can't do that with the C++ library. They all start running. So here's the thread priorities, and sure enough, there's 7 of them, and sure enough, the idle is lower than lowest, and time critical is higher than highest, and away to go. So now, let's talk about C++. Finally, let's talk about C++ library. So we create a thread. We can create a thread this way, TF. And this assumes there's no arguments. Now, but we can also create a thread. If I have a function G that takes some number of arguments, A1, A2, and maybe something else, I can just pass it G and pass it those arguments. This is using this function is a variadic template function. We haven't talked about variadic templates. I will talk about them, but probably not until very close to the end of the course. We didn't have time. We ran out of time when we were talking about templates. Variadic templates are a way of defining a function that takes an arbitrary number of arguments. It's really useful. Threads use it, and occasionally you would want to use it. So that's the way that works. And these are passed by value. If they were passed by reference, the thread is manipulating that A1 argument, and your main program could be manipulating that A1 argument, causing race conditions. So it's passed by value. There is a way to pass it by reference. We'll see on Thursday when we look at code examples, but you do that very carefully, understanding the consequences. So it's easy to create them, and it turns out that you can pass it, not only can you pass it unbound functions like G, but I can pass it a member function of a class, and so I pass it a function pointing to the class, and the next argument is the address of that object that I want to run that function on. Again, we'll see that in examples when we look at code. So C++ provides for getID, join, or detach. So now every thread that you create with the C++ library must be either joined or detached before you leave the program. If you forget to do that, the program will throw an exception. By intent, it was designed that way. The model is that join, your execution, your main won't quit, won't exit before that thread is done running. So join blocks until the thread finishes running, and now you can exit the program. Detach allows that thread to free run. It's like a background thread, okay? And it disassociates the thread object from the underlying operating system thread, okay? So, and you must call either one or the other, and you may not remember, did I call them or not? There is an isJoinable thread function, and so you say if isJoinable join, or if isJoinable detach. Okay, and so if it's already been joined or detached, no harm done. But if it hasn't, you've saved the day. Okay, so and that, you know, usually is only there's code in several places that are interacting with that thread, and you don't know whether it's been. So you just call isJoinable. And there's a standard this thread sleep for some chrono duration, you know, chrono 15 milliseconds or something.
Professor?
Yeah.
In case of detach, the thread will get detached from its parent process? The thread will get detached from its parent process?
Detach disassociates the object with the underlying operating system thread. The underlying system operating thread will continue to run, and if I exit the program, that thread will die a horrible death when the program dies. The normal model is normally, if I'm in a GUI that's, you know, up and running, I feel free to detach threads. In a console application, I may not choose to detach threads because the thread may not finish before I exit. Okay. You'll see lots of examples from me. You know, I use them both at different times, and we can talk about when that's appropriate. So often we need to share resources. So here's a case where we use a share thread-safe blocking queue to share. So a parent sends messages to child thread, and if the child thread needs to talk back to the parent thread, it just has another queue that sends messages going the other way. It works fine. You know, really nice way to communicate. There's other ways to get results back and forth from a thread, and we'll see some of that on Thursday. Synchronization, so program may need multiple threads to share some data, so we need to control it so that that shared stuff doesn't get corrupted. So one thread accesses the data, you know, blah, 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 blah. We already talked about that. So the process of making access serial, allowing only one thread at a time to access that code, is called serialization or synchronization, and we do that with a lock. The basis for that is in the Win32 API. There's two functions, wait for single object, that what it does is it waits on the object handle for a given period of time, and one of the periods of time is capital INFINITE, means it'll wait forever. And I strongly recommend that if you use this, you use infinite, because the model here is you're waiting for this object to enter the signaled state. And if it times out, it hasn't entered the signaled state, so what are you going to do? Okay. Maybe go off and do a little work and come back and wait again. And if it falls through, go on and do a little more work, come back and wait again. That sounds complicated, as it is. You'll never get it right. Don't do it. INFINITE, infinite. You can wait on multiple objects, and so you can pass an array of handles, and this is the size of the array. And an fwait parameter says return if if f-wait is true, wait for all the objects. If it's false, wait for the first object to become unsignaled. You might use false to build a semaphore. Okay. C++ library doesn't have a semaphore. One of these days I'll build one. So here's the Win32 thread synchronization. Interlocked increment is an atomic incrementing or decrementing of any integral type. That means an int, a short, a long, long, pointer, you know, all of those. Critical section is a lock, but it doesn't use a kernel object. It doesn't wait on single object handle. It's only good inside a single process, but it's lightweight because you're not making a thunk down into the kernel to access the kernel resources. Mutex is a kernel object and does system-wide locking. So, and event is a kernel object. Semaphore is a kernel object. Slim reader writer lock, I think, is based on the critical section. I'm almost certain it's based on the critical section. Slim reader writer lock, the way that works is it shares reading access, but each writer gets exclusive access to that shared resource. And there's an API that, you know, works fine for it. That's, it can be useful. Condition variable is really useful, really important. I'm going to reserve talking about it until we talk about my blocking queue, because I use this in the blocking queue. Okay, there's something very necessary that happens here with that condition variable. Very useful. Okay, C++ 11 synchronization has a standard mutex. As far as I know, I don't know if they wrap the condition variable anywhere. If so, I suspect that sometimes the mutex will wrap a critical section and sometimes it'll wrap a kernel object. I don't know. The reason I don't know is A, I wasn't part of the design team, so I don't know. And B, I've done some performance testing on it, and the mutex's performance seems to be slower than I would expect for a critical section, but faster than I would expect for a kernel object. So, you know. But anyway, there's variations on standard mutex, time mutex, recursive mutex. So time mutex just uses the, you know, non-infinite binding time, and don't use it. Don't use it. But recursive mutexes can be useful if I have a function that takes a lock, and that inside the lock it calls another function that may take a lock. Okay, I can throw an exception. The library will throw an exception if I haven't used a recursive mutex, and that's just to prevent deadlock. You know. So I take this lock and I can't, you know. Recursive mutex, I've used it 2 or 3 times in my life, okay. But when you need it badly. So you try really hard, if you take a lock in some code, you try not to call other code from within that lock. But you want it to be as small a region as you can for performance reasons, and B, calling code from inside a lock is a great way to have deadlock or recursive locking problems and stuff like that. So your model is not to if you can help it. LockGuard is an interesting lock. It doesn't have a lock and unlock function calls. The constructor acquires a lock and the destructor releases a lock. So the way you see it used, at the end of a program, we have something that we want to, at the end of a function, we have something that we want to provide shared access to. We just declare the lock. We don't seem to ever use it. And then, so what happens is the construction locks it. And then when we leave the function, this destructor is called and unlocks it. Okay? Pretty nice. But every once in a while, you know, we can do that inside an anonymous scope to control when the lock and unlock occurs, but that can get a little clumsy sometimes. There is a unique lock that is just like standard lock. Constructor and destructor work the same way, but also there's a lock and unlock. So you can tell the unique lock, don't take the lock on construction, or do take it, and you can also call lock and unlock. And if you call lock when it's currently locked, it just ignores you, you know, because it's already locked. But There's places, for example, some other function needs to ensure that this thing is locked or unlocked, then you need to use unique lock. Shared lock is a reference counted lock. Condition variable wraps the operating system condition variable. And again, we'll talk about this when I talk about my blocking queue. Atomics wraps the atomic incrementing, you know, I'm not pulling the name out, but anyway, it's a atomic. Future is interesting. We can return a future from a function. So the question is, it's easy using the C++ library to pass functions, to pass arguments to a thread function. How do we get the result? It's not so obvious. One good answer is with a future. A future blocks until the thread is ready, until the thread is done, and the thread does something to cause that future to unlock. So basically, you'll call this some asynchronous function, some function that's going to run some code asynchronously, and you go off and do a whole bunch of stuff, or maybe you start up 4 or 5, you know, maybe I'm analyzing stuff in a file, I might do a whole bunch of those, okay, and then and I just return futures, and then I'm willing to block because all those things, all those child threads are running concurrently. It's fine for me to block because there's, you know, lots of stuff going on. But then when an answer is ready, then I can. So if the thread is not done yet, I'll block. There's a future called get result or get value. It's get value, I think. When I call get value on the future, it will block unless the thread is finished. If the thread is finished, it will fall through, and it returns the result. So a really nice mechanism. There's a corresponding thing called a promise that's used by the asynchronous function internally. The promise and the future are linked. Inside the function, a promise is created, and then a future is created that calls get promise. No, it calls, I'm sorry, the future calls get future on the promise, and that links the two together. And now what happens is, until the promise calls set value, that future will block. But once the promise calls set value, now the future unblocks. And so inside that function, you know, a promise has called set value, and now the future is available and ready to use. And we'll look at some code on Thursday that does all those things. Okay. So promise and future are linked. Normally, we use futures a lot. We very rarely use promises because there's a package function that does that for you. You know, you had a question?
Yeah. Can you repeat the part where you said unique lock is movable but not copyable?
Yeah. So what happens are there are kernel objects that, for various reasons, that can't be copied. And so if it's using it, like a mutex can't be copied. Okay. And so the wrapper around it is movable. It can transfer ownership of that mutex to somebody else, but we don't want two people having ownership to that same mutex. Right? Not a good idea. Okay. So for that reason, it's assignable, but not. So I can transfer ownership of that lock to another thread, but I can't copy it. Okay, wow. We've covered a lot of territory. So there's an appendix here that has you know, some stuff about the Win32 API. So I'm going to make a contract with you. If I can get my pointer back, yeah, I'm going to make a contract with you. On the midterm, I will not ask questions directly about the Windows threading and synchronization APIs. Everything you need to prepare for the midterm is in this folder. And you say, good. You look inside the folder and you see a solution with 13 projects. Okay? And that's what we're going to look at on Thursday. We're going to go through all that on Thursday, every bit of it. Okay. So by the end of Thursday, you should be prepared for the midterm. There will be threading questions on the midterm. There will be questions that ask you to write. Every exam will have a question that asks you to write threading code. And at least a couple of them ask secondary questions that don't necessarily ask you to write code, but ask you questions about threads. Okay. So, but if you understand what's in that folder, and I'm going to walk you through it on Thursday. That's my main job on Thursday, is to walk through this, to look at the blocking queue, and to look at tasks and thread pool. The blocking queue and the task and thread pool, these are classes that I wrote, Okay. They're not part of the standard API. Turns out they're fairly easy to write. They're not very complicated, you know. So we're going to do this, this, and this, and for the midterm, you need to know this. For project 3 and 4, you need to know this real well, and you need to know this. You may need to know this. Okay. So on Thursday, we're going to look at the concurrency folder, and if we have time, we'll look at the blocking queue and the thread pool. If we don't, on Friday, I will answer questions about threading. I will answer questions about the midterm, and then lowest priority, above idle priority, but of those 3, lowest priority will be project 2. Okay? But I will answer questions about project 2 if you have them. By now, I'm hoping that most of you don't have, lots of outstanding questions about project 2. Yes, question.
It's a future function, a callback function. Can we do
No, it's not a callback. There are ways to do callbacks, and you'll see some examples of that. But it is not a callback. It is an object that wraps the result of the thread computation.
The only thing we can do is get the value back.
Only thing you can do is get the value back. There are ways to do callbacks, and I'll show you how to do that. Okay? I don't promise you that I will show you how to do that, but if I don't show you how to do that on Thursday, it won't be on the midterm. I may have to go and doctor. But I think, do me a favor and send me an email tonight that said, will callbacks be on the midterm? And I won't answer that question, but what I will do is I will try, just send me an email saying, can you talk about callbacks on Thursday? And if we have time, I'll definitely talk about them. I may actually have a callback example in C++ 11 concurrency. I'm not sure that I do, but I'll try to. Callbacks are very useful, and we use them all the time. Any other questions? I'm tired. We've covered a lot of ground. Okay, so I'll see you on Thursday, and I'll see many of you on Friday.
Okay, I tell you what, wait until you come in
怎样？
有没有去商量旅游的事儿？
要不要也去？
我也去。paper， 对，是吧？啊，我让齐静写一篇，然后我跟他一组，然后我就放给他。不是说两个人，不是？哦，好像是。
来，我说的是。
没课你们要去听吗？
哦，回来看，我收到的短信，告诉我他在说考一点新的问题，主要是考这第三个。但是那个螺丝针，看，一看我也知道我得在哪里。我关心这个，我今天想赶快把 O 和 D 排一点去，找不到。今天是9的写。我要是我买到的，后来我上高中就去那个济南小楼，他在这儿，做完之后他立刻调到这个，就这个家放在这儿，因为这个全都是比较，他在另一个地方，就是所有的都是这家第一好卡，然后你改和比较，他就是这么简单的，就是 X 路的。相当于他第一方我在整个流程都是他写好的那个，然后他给你们告诉做你很多的结果是，然后我打电话问他那种流程是他这个地方没有问题，但是我就看不到地方。那他们不靠谱，买那个东西。我昨天打客服打到2点。而且特别烦，就是不是啊，因为这个东西就是我是从前。